Hey guys, welcome to the second video for chapter 8. So I want to finish up the ideas from the inverse trig lesson, and then I'll do the second part, which is solving trig equations. Okay, so we left off with this problem. What if your angles for doing inverse trig don't involve nice values or not special angles? So for example, if this was like cos of pi over 4, then you could do this problem easy. If it's not an angle that you know, we got to do a little bit more to solve. So let's take a look at that. So the first thing that I would do is I would say to myself, okay, I need to create this triangle that's 8 pi over 13 because I don't know it. That's kind of one of our normal things that we do. All right, well, let's figure out what quadrant that's in. This is pi or 13 pi over 3. We've got 0, pi, and then halfway would be about 6.5 pi. I'm putting this here so that you can figure out what quadrant this should be in. Some of you might automatically know, oh, that's in the second, but okay. Now remember, this part is 8 pi over 3, or 13, excuse me, but I want to know the angle inside the triangle that I'm going to use. So I'm going to use 5 pi over 13. Oops. So that's my little reference angle. Okay. So now, what do I know about this triangle? Well, I know that the sides could be labeled y, positive y. This is a negative x value. That is important that I think about it as being negative, and then I'll just call that the radius. Okay. So now that I have the drawing and I can tell who's supposed to be negative, which is just this x side, I need to think about, well, what would the cosine of this triangle give me? So the cosine would be the adjacent, which is a negative x value over the radius. So now you're kind of trying to find this. So you're trying to find an angle that gives me this, but for the sine ratio, guys. So here's the easy way to do that. If you want the sine ratio to be this, that means you want the opposite to be this value and the hypotenuse to be this. So look at this triangle. You can't use this angle, but if you use this angle, then the opposite over the hypotenuse would be negative x over r. So that's what we're going to do. We're going to use this guy. So how do we get that guy? Well, these two should add up to 90, or in radians, pi over 2. So I'm just going to do pi over 2 minus that given angle to get this missing one. Okay, so yeah, I have to do a little converting. Common denominator business. So that means that angle is 3 pi over 26. Now, you have to think of this though, because you need to know, you need to get out, because this guy was a negative, you need to be able to get out, use an angle that will give you a negative. Well, for sine inverse, you can only be negative, or sine inverse only exists in first and fourth, right? Capital sine inverse. Which one would give you a negative value? The fourth. So what angle am I going to use? I'm not going to use positive 3 pi over 26. I'm going to use negative 3 pi over 26. That angle would give me the same ratio as what the cos did of this triangle. So my final answer would be negative 3 pi over 26. And we can try a couple more of those in class. Okay. What if your problem uses letters rather than numbers? So we saw this happen in chapter 7, where we started to introduce, well, what if it was just arbitrary values? You're going to treat this the same way. You're going to come up with your triangle, and then you're going to solve. The first thing I would do is think of this as sine. An inverse trig function is an angle. So I'm going to use this relationship to get the angle. So what do I know about that? Well, I know that the cosine is x. But remember, technically x is x over 1. So I'm going to draw my little triangle, and I'm going to say, okay, the cosine is x, which is adjacent over hypotenuse. I'm going to use Pythagorean theorem to get this side. And then all I need to do is get the sine of that same angle. And the sine of that same angle is opposite over hypotenuse. Now, how did I know that it was in the first quadrant? Well, remember, capital arc cos would be positive. So you only have, if this is a positive number, which if it's negative, it takes care of itself. We can talk about that more in class. But I know that it would be in the first or second. And since, again, we can talk about those scenarios as far as of answering that correctly. Okay, down here, we've got sec of arctan. So I want the sec of this relationship. Again, I'm going to treat this as x over 1. So I'm going to create my tangent relationship, opposite over adjacent, get the hypotenuse, x squared plus 1. Technically, it was x squared plus 1 squared, but you shouldn't write 1 squared because that's 1. And then I want the secant. Secant is hypotenuse over adjacent over 1. Okay, let's keep going. What about this type of a problem? Now, this one looks crazy, but let me help you break this down. This is an inverse function, and so is this, but they're two different ones because they have different relationships. So remember, what do inverse functions give us? They give us out angles. So I'm going to call this angle theta, and I'm going to call this angle beta. Oops, that's a minus, sorry. So you really have this. Now you guys know that there's a way to expand this so that you can deal with each angle separately. Your sine subtraction. So sine cos minus cos sine. So now if you could create triangles for theta and beta, which you can because you have relationships, you can plug stuff in. So let's do the theta triangle. The theta triangle, I know that capital arctan is 4/3, it's positive. Arctan can be in 1 or 4, so since it's positive, it's in 1. Opposite over adjacent, hypotenuse, Pythagorean theorem, 5. For my beta triangle, I have a negative and it's cos inverse. Remember, cos is allowed to be, capital cos inverse is allowed to be in 1 or 2. Since it's negative, it's in 2. I have adjacent over hypotenuse. The 12 has to be negative because the radius can't be. Pythagorean theorem, this is a triple. That ends up being positive 5. Again, be careful that you're making everything, the correct value. Okay, then it's just plug it in. This is almost like last unit. Sine of theta, 4/5. Cos of beta, negative 12/13. Cos of theta, 3/5. Sine of beta, 5/13. So we get negative 48 minus 15. These both end up being over 65. So negative 63 over 65. So very similar kind of to what we did last time. Okay, so the natural progression would be, how do I deal with it when it's variables? Same way. First thing I would do is rewrite this as this is an angle and this is a different angle. Then I would expand using the identity. And then I would create my triangles. So my theta relationship is the arc sine is x, arc. Remember, x is just x over 1. So opposite over hypotenuse, the missing side would be 1 minus x squared. And for beta, I have the cos, arc cos is y, and that's adjacent over hypotenuse. So then the tan, again, I just have to fill stuff in. So the tangent of theta is x over root 1 minus x squared, plus the tan of this guy is root 1 minus y squared over y, and then 1 minus their product. Now, some of you could have done a better job on the last test of reducing. So let's look at this. You need to at least get it to a point where it's 1 fraction over 1 fraction and then multiply by the reciprocal. So let's look at this. Here, I'm going to do common denominators. So like this guy needs a y, and this guy needs a root 1 minus x squared. So on top, I have xy plus, technically those can both be in 1 square root, so I'm going to go ahead and do that, over the common denominator. On the bottom, the common denominator is going to be this. So this guy's going to need a y root 1 minus x squared on top and bottom. And the good news is it's a 1, so like that makes that easier. So then on the bottom, I have y root 1 minus x squared minus x root 1 minus y squared, all over the common denominator, y root 1. See? Look how nice that is. When I go to multiply by the reciprocal, those two are going to cancel, and I'm left with something that's at least a little bit more reduced. Now, I could go further here and mess with conjugates of the denominator, but for our purposes, this is fine. If you want to practice going further and using the conjugate at the bottom, you'll see how you can reduce it a little bit more. But this is fine. Okay, so that's the end of the inverse trig lesson. And then the last part of chapter 8 is literally solving trig equations. Okay, so when solving trig equations, guys, it's like I said, it's super short. It kind of uses what we had done with proofs as far as simplifying and using identities and things like that. But we're looking for values that make our equation true. So this time we're dealing with equations, which means we can do things to both sides. So let's take a look at that. Maybe this one seemed to go away. There we go. I said the textbook does kind of take the snide approach of saying there are no general rules, and that you can just do some examples, but I think we can find some. And Paul Forster, who we've used his worksheets before, talks about some good rules. So we're going to go through those first. Okay, so some rules for solving equations. Number one, you're going to want to get an equation in which there's one function or one argument used. And what I mean by that is like everything's in terms of just cos, or everything's in terms of just sine or tan. Some of the ways that you can do that are using identities to reduce. You can substitute double or half angle functions. Obviously, sometimes it's just doing algebra, like putting things together. This is a biggie. You should never divide by a factor that has a variable. So we're going to talk about that. That is a big deal. Like you should never divide both sides by cos or something. And then, of course, you can factor things apart so that each part maybe only has one trig function. So that's kind of an idea. Once you get that, then you can find your solution by getting the angles that work for that. And again, it depends. If it's a special angle, you can do that. You can get it exact. If it's special, if it's not, we'd have to use our calculator. Most of the time, there are two angles that work. If I'm asking you to give me the solutions from 0 to 2 pi, not always, but there usually are two solutions that work. And then, like we said, do any algebra that's needed to continue, like if you have a double or half angle, and then write the solution set and test the solutions, because sometimes they are extraneous. Okay. We'll also talk about generalizing our solution. So again, I introduced this first, but you will see it in practice, but these are some main ideas. So if you want to come back to these later in the video, you could always rewind and come back and look at those. So let's look at some actual examples and practice it. So I'm going to start very basic. So maybe this is our equation. 2 sine x equals 1. Okay, we're going to solve it for one wrap and then all real numbers. So this is like, sometimes we call this the general solution and this the particular, because we only are using a particular wrap of them. Okay, well, if you wanted to get x, I think most of you are comfortable saying that you would divide both sides by 2. And then technically you're doing the sine inverse of both sides. But most of you can just kind of see this and think to yourself, okay, what angle gives me 1/2 for sine? So I tend to draw my little coordinate plane and think about it. So sine is 1/2, which is the opposite side and since this is in terms of 0 to 2 pi, we're going to have to do radians. So it's 1/2 at a pi over 6 reference angle. Where else is sine 1/2? Also in the second. It's also positive in the second, so 5 pi over 6. Those two solutions right there would be your particular solutions, because those are the only two solutions that work for one wrap around. So notice I put them in a set, and I said those are the two that work. That's the particular set of solutions. Now, what about all real solutions? All real solutions would just be any wrap of each of these. And since unfortunately, they're not evenly spaced, so what you could say is pi over 6 plus 5, pi over 6, comma 5 pi over 6, and then plus 2 pi n. Why plus 2 pi n? This would wrap each of them full circles. So then this gives us all versions of the answer. Okay. Let's go a little bit more difficult. So notice on this one, I put a triple angle inside. You do not need to use an identity. If there's only one trig function, I'm going to show you how you can solve this with the 3x still in there. So I'm going to treat this as normal. And I'm going to start with what we just got. Whoops. which is that if you took the sine inverse of both sides, you'd get that the angle, which is still 3x, choices for the angle were, I think we said pi over 6 worked, we said 5 pi over 6 worked, right? And technically, guys, you could keep going. Now, I'm going to keep going for a reason. So if I wrapped these back around the circle, I'm going to do a little guy up here. If I wrapped pi over 6, so I'm going to add 2 pi to that. So that 2 pi in terms of 6 would be 12. So I'm going to add 12. My next version of pi over 6 would be this. My next version of this would be 17. I could keep going on. Okay, I just keep adding 12. So I could keep going on and on and on. And I'm going to do a few so you can get a feel for this. So again, I'm just adding 2 pi. So these were my original primitive solutions or principal solutions, and then these are just me adding wraps of them. So then this guy is 29 pi over 6. I'm going to do 2 more wraps, or 1 more wrap. So add another 12, I get 37 pi over 6, and then 41 pi over 6. So these are just wraps of this solution of sine being 1/2. Normally, we would only use this. This fact that we're setting it equal to 3x is what's causing me to list more, and I'm going to show you why. Well, what would you do next to solve this for x? Because you haven't solved it for x, you've solved it for 3x. Yeah, you'd divide by 3. So that would actually turn these all into over 18s. So if you need the particular solution 0 to 2 pi, this is no longer 0 to 2 pi because now they're over 18. So I have to figure out where is 2 pi, where does that stop within here? So let's take a look. I'll keep going with all of these over 18, and then we'll see if we can figure it out. Okay, so what is 2 pi in terms of 18ths? Well, we can just do a quick conversion, times 18 times 18. So 36 pi over 18 would be the same as 2 pi. So anything over 36 is out. So those two are out. So let's look at what happened. It looks like these first ones were included. This was the first wrap. This is me wrapping it a second time, and this is me wrapping it a third time. That is no coincidence, guys. If your coefficient over here is dividing by 3, I'm going to have to do that many wraps so that when I divide by the 3, it still fits from 0 to 2 pi. Another way that you can think about that is this. If you want your x's to go from 0 to 2 pi, rewrite your domain. That means your domain has to go from times 3 times 3. This would be 3 times around. So again, any solution you get at the beginning, you have to wrap it 2 more times in the sense of like, I need 3 total wraps of the solution. Okay, we're going to do a bunch of those so you'll get more comfortable with that. Okay, so these are all the particular solutions. Now, what if we wanted the generalized solution, this part? If we want the general solution, well, let's see if we can see a pattern. There's 4 pi over 18, 4 pi over 18 between those two. Then there's 8 pi, then 4 pi. It looks like we can't do 1 for all of them, but again, we can usually do it with the first 2. Because in the first 2, I added 12 pi over 18, 12 pi over 18. So it's these first 2 guys. Oops. Comma. Plus 12 pi over 18 n. But I can do a little better than that because I can reduce the 12 pi over 18. So I would probably write this as pi over 18 and 5 pi over 18 wrapped, let's see, reduce that by 6, 2 pi over 3 n. Again, adding this much is how I go from here to here to here to here to here, and so on and so forth. So particular would be these 6, general would be these guys. You only need 1 of them. Okay. And then this question right here, I just wanted to show you guys this. If I start off with it equal to 0, is just the same problem we just did. I would have to move the 1 first and then divide by the 2. I just wanted to show you, obviously, that's the same idea. Okay, so these are pretty easy, but they did introduce a triple angle, so you could kind of see that. So let's go into something that's a little bit more difficult. So let's say we did this, tan of x plus cotan of x equals -2, and we want to solve this guy. So this is a little trickier because I'm dealing with trig functions that aren't the same. I have two different types of trig functions. I can do something similar that I would have done with proving, except remember this is an equation, not a proof, so I can do things to both sides. So what's the relationship that you notice between tan and cotan? They're reciprocal functions. So I know that if I multiply both sides of this equation by a tan x, then I can put everybody in terms of tan. So what I mean by that is this would become tan squared x, tan times cotan would become a 1, and this side would become a -2 tan x. Now, suddenly, everybody is in terms of tan, which is one of the things we said. If you can get everybody into one trig function, it can make it a lot easier. So I'm going to bring everybody to one side. So I'm going to add that to tan x, and I'm going to solve. Now, I would say 95% of the time we end up factoring, especially when we have something quadratic. If the fact that this is tangent is bothering you, you can do substitution. Let's let u be the trig function tan. Then you could express this as u squared plus 2u plus 1. Then you could factor. Some of you are more comfortable with that. Eventually, hopefully, you don't have to use the u substitution and you can factor with trig, but for now it's fine. So then let's factor. This factors into u times u, has to be 1 times 1, and they're both positive. So set them both equal to 0. Technically, I only need to do 1 because it's going to be the same thing, and I get u is -1. But remember, we weren't solving for u, so we got to put back in what we knew u to be, which is tan x. So we're looking for when tan x is -1. Tan is 1 out of 45, or a pi over 4, but it's negative, so that would be in the second and fourth, which are 3 pi over 4 and 7 pi over 4. So if I want my particular solutions, I would say x equals 3 pi over 4 and 7 pi over 4. Oops. Now let's make sure that they work. So I'm going to actually plug them back in. I did not do that earlier. I should have. So if I plug in 3 pi over 4, let's make sure we get out -2. Tan of 3 pi over 4 is -1. Cotan of 3 pi over 4, also -1. So yep, that one works. 7 pi over 4 is a -1 plus a -1. Yep, also works. You always want to make sure they always work. So that's the particular one wrap. What if I wanted the general solution? Well, this one is nice because this one, they're evenly spaced apart. How far apart are they? Pi. So instead of having to do each one and saying plus 2 pi n, I can just say this one plus pi n. Cool. All right. I think that's the only one. And then this one, yeah. And then we'll talk about the calculator ones in class. Okay, let me just, I'm going to throw one more at you guys so we can just see something else. Let's do, maybe I have sine x cos x minus 2 sine x cos x minus √3 sine x. Yeah, I'm going to do this. I'm going to change it slightly because I can make it a little bit more fun. Let's do this. Should work. I'm making it up, so we'll see. Okay, so let's say that you had this question. First of all, the nice thing about this problem is that everybody's in terms of sine. The not so nice thing is that you're dealing with two different types of angles, and we can't solve that unless we can separate them, and we can't factor them apart. So you're going to have to use the identity. And the identity for sine 2x, you guys should know that. I just did it, so you can see that. This becomes 2 sine x cos x. Okay, now you might be saying, well, that's not helpful because now we have a cos. That's true, except also a technique that we are learning is that you can factor out or factor apart the trig functions. So for example, I can factor out this sine, and then the two trig functions will be separate from each other. See that? What do we know about a product set equal to 0? We know that it will be true as long as each part of the product is 0, or when each part of the product is 0. Okay. Sine is 0. Let's think about that. Sine is 0 here and here. This one is technically really saying cos x equals root 3 over 2. Cos is root 3 over 2 at a pi over 6. And careful, it's also positive down here. So that would be 11 pi over 6. If the question asks you to go from 0 to 2 pi, you cannot call this one negative pi over 6. That wouldn't fit. So just pay attention to that. We'll do the particular and then the general. So I need this guy, and those two. These two are evenly spaced. These are not. It's up to you how you want to write it, and it's fine. Doesn't have to be super concise. I'm going to do these two first. So this would be 0 plus pi n, or I can just say pi n. And then I also have this one. These are not evenly spaced, so I would have to do them separately. So I would say pi over 6, comma 11 pi over 6. So those are my first, oops, I didn't mean to do pi n. I forgot we were doing, I was doing the general solution, sorry. The particular solution would be just going around the circle. So, sorry. So I have 0, pi over 6, pi, and 11 pi over 6. And a lot of times I'll put these all on one, just so you know, but I was showing you them separate because I like them to go in order. They should go from lowest to highest. So 0, then the pi over 6, then the pi, then 11. Okay, that would be my particular. If I wanted to do the general solution, this is where what I was starting to do a second ago. That would be, these two are 0 plus n pi, or just n pi. And these two, which are not evenly spaced, so I'd have to say like pi over 6, comma 11 pi over 6, and then both of these plus 2 pi n. Cool? This would get all of those. This would get all of these. Don't forget to say n is an integer. Okay, this is what we're going to get more practice on. I mean, this is where we're really going, guys. So knowing your identities, knowing, how to find these guys, super important. We're going to get to practice a lot more. This is a pretty short chapter. I mean, this is it. This is the second half. The first half is all about solving, and the second half is all about, I'm sorry, the first half is all about inverse, and the second half is all about solving. Okay, good luck.